Everyone.
Yes, sir.
Yes, sir. Okay. So, in the last class, we have discussed how one can apply CFD techniques for the solutions of flow problem. Like that is, if there is a flow phenomena, if the fluid is flowing in a pipe or fluid is flowing through a conduit or any industrial vessel, how one can apply CFD techniques for the solution of a flow problem. Now, to understand how one can apply the numerical techniques for flow problem, that primarily we are interested to solve the governing equations that governs the fluid flow problem is Navier-Stokes equation. That is a three-dimensional nonlinear partial differential equation. So how one can apply numerical techniques for the solution of three-dimensional nonlinear partial differential Navier-Stokes equation, set of Navier-Stokes equation, that is x momentum equations, y momentum equations, and z momentum equations, in addition to that of continuity equations. Since in this course we are primarily interested to solve two-dimensional cases, that is the scope of this course, so we will be adhering to the situation when we are interested primarily in solving two-dimensional flow problems. So for that, we have started a discussion that there is a popular method which considers for the solution of two-dimensional flow problem, that method we call stream function vorticity method. That is the method basically how we can apply the stream function and vorticity method for the solution of nonlinear partial differential equation, which is basically the Navier-Stokes equations. So we are interested to solve the flow problem. We interested to imagine, or we interested to generate the streamline contours or velocity contours, and how the pressure is getting distributed along different planes in a flow, two-dimensional planes in a flow. So if we want to compute such situation based on certain sets of boundary conditions, for that we may apply, or we can apply, stream function vorticity method, which is very efficient method, and with that method one can capture the fluid flow problems inside any industrial vessel or any two-dimensional computational geometry or two-dimensional geometry. So the limitations of this method is that since we are applying stream function method, that is that the format that by introducing stream function for the solution of partial differential equations, and the existence of stream function is only limited to two-dimensional cases, so that the one of the limitations of this method is that we cannot apply this method for three-dimensional situations, because in three dimension there is no existence of stream function. Accordingly, we have seen how we can generate. So basically we have to generate the vorticity equation and the stream function equations. So if we can generate the vorticity equation and stream function equations, why you are primarily interested to generate vorticity equation and stream function equation? Because we have seen that in the momentum equation, that x momentum and y momentum equation, that is the x momentum equation here and y momentum equation here, there is an additional term which is the pressure gradient term, x pressure gradient and y pressure gradient. Since we don't have any additional equations for the pressure, so in the stream function vorticity method, what we need to do, we need to get rid of this pressure gradient. So if we want to get rid of this pressure gradient, what we have seen in the last class, that we differentiate the x momentum equation with respect to y, and differentiate the y momentum equation with respect to x, and subtract the resulting form of those equations to obtain a vorticity transport equation, where vorticity zeta, which is defined as del v del x minus del v del y, or minus zeta equal to del v del y minus del v del x. So basically this is a two-dimensional vorticity that already we know from our fluid dynamics class, kinematics class, that we can define the vorticity as a velocity gradient, function of velocity gradient. From this definition we have obtained the vorticity transport equation. That means if we could solve this vorticity transport equation, we could able to generate what is the pressure field, or what is the velocity field, and what is the stream function field inside or through a two-dimensional flow domain. So that is the situation that already we have discussed and already we have seen. Today we will be focusing that already we have generated the vorticity equation, or we have derived the vorticity equation. Today we will be our focus will be to derive the stream function equation. That is the second equation. So first equation is the vorticity equation, and second equation is the stream function equation. So here we have seen this vorticity equation is nothing but a time dependent equation. It is a transient equation. There is a del zero del t term. There is a similar form of Navier-Stokes equation, but it is a convection diffusion equation. This is a convective term, and this is the diffusion term, and this is the transient term. So this equation is nothing but the convective diffusion equation for the vorticity. Now, what we will be interested in? We will be interested in formulating the corresponding equation for the stream function. For that, what we will be doing? So we know from our fluid dynamics knowledge that we can define stream function as its function psi, which is function of x, y, z, and t, but if not z, x, y, and t, function of space and time. So we can define stream function as v equal to minus del psi del x and u equal to del psi del y. These things already people know from your fluid dynamics class. Now what we have defined, that this stream function equation automatically satisfies the continuity. That also we have seen in your, I think you must have done in your fluid dynamics class, that stream function is defined in such a way that it should satisfy the continuity. It should automatically satisfy the continuity. So in this context, it is appropriate to mention here that for a flow to happen, that any fluid flow situation, it must satisfy the continuity equation. Without satisfying the continuity equation, fluid flow is impossible. So that is the primary criteria of fluid flow. So accordingly, we have defined the stream function. The stream function will be automatically satisfying the continuity, because if you take derivative del v del x del y plus del u del x, which is the continuity equation, that will be zero. So if you can take derivative and add those two derivative terms, it will be zero. That means it is automatically satisfying the continuity equation. Now what we have seen, we have defined the vorticity field, that is minus zeta equal to del u del y minus del v del x, that already we have seen in the last class. Also we have discussed today few portion of it. Now, so what is del u del y? That is minus zeta. We can write, if you replace or if you can substitute u with del psi del y and v with del psi del x, it's very simple and straightforward. You can see what we are doing, is minus zeta equal to del u del y minus del v del x. What we are doing, we are substituting u with del psi del y, that is del y of u equal to del psi del y minus del v del x. So del x of v equal to minus del v del x. So del x of minus del psi del x. That means del 2 psi by del x2 plus del 2 psi by del y2. That means if you can write del 2 psi by del x2 plus del 2 psi by del y2 equal to minus zeta, which is basically your vorticity. So we can write this equation as grad square psi equal to minus zeta. So this is the equation of your stream function. So we have derived the stream function from the definition of vorticity, that is grad square psi equal to minus zeta. So this is very straightforward. I think everybody must have understood how we have derived the stream function equation from the definition of vorticity. Okay, I think this section is clear now. How we have derived the stream function equation. Any doubt? Does anybody have any question? Is it clear?
Yes, sir.
Okay, very straightforward. Very straightforward. Uh, okay. Okay. Now, therefore, we can write that we can write that we have two sets of equations. One is our stream function equation, that is del square psi equal to minus zeta, del square psi equal to minus zeta, that already we have generated or already we have derived, del square psi equal to minus zeta, and your vorticity transport equation, that is rho del j del t del j dt equal to mu grad square zeta. So this is the two equation which is basically consist of stream function vorticity method. So in the stream function vorticity method, basically we primarily solve these two equations to obtain the stream function, and accordingly if we can obtain the stream function, you can also obtain the velocity field, right? Now for inviscid flow, that is where the viscosity is zero, now we can write for inviscid flow where the viscosity is zero, so your vorticity equation will be simply d zeta dt equal to zero. Simple vorticity equation, d zeta equal to zero. Now for a steady inviscid flow, that means if d zeta dt equal to zero, for a steady inviscid flow, when the flow is steady, it is not time dependent. It is zeta equal to constant, right? If it is not steady, if it is not time dependent, zeta equal to constant along a streamline. That we can easily understand from this equation. For a steady inviscid flow, zeta equal to constant along a streamline. So along a streamline, for a steady inviscid flow, zeta is constant. Now for irrotational flow, where vorticity is component is zero, right? When we have a irrotational flow is irrotational. Already you have studied in your fluid mechanics 1 class probably. For irrotational flow, so zeta equal to zero, so we can substitute zeta to be zero for irrotational flow. So we can write this equation as grad square psi equal to zero, irrotational flow. So therefore for rotational flow, which is nothing but your stream function vorticity method, so grad square psi equal to minus zeta. These are very straightforward and can easily be understood from your fluid mechanics knowledge. So that we can basically, these are the logical extensions of these two stream function and vorticity equations. Now let us do some further calculations. So what is the calculation? Calculation is, so what we have understood from your vorticity transport equation. So this is the vorticity transport equation. You can write vorticity transport equation as rho del zeta del t plus u del zeta del x plus v del zeta del y equal to mu del 2 zeta del x2 plus del 2 zeta del y2, that is equal to mu grad square zeta. So this is the equation. What I am doing here, I am simply expanding this equation. So what we have derived in the last class, I am simply expanding this equation as d zeta dt is a substantial derivative of this function vorticity is zeta. So rho d zeta del t plus u del zeta del x plus v del zeta del y equal to mu grad square zeta. Now what we will be again doing? We are simply substituting u by del psi del y. So we are substituting u with del psi del y. So equal to del psi del y. So v equal to minus del psi del x that we have substituted here, plus equal to mu grad squared zeta. So what is zeta here? Zeta equal to minus grad square psi. So this zeta equal to minus grad square psi. So what we are doing? We are substituting the function zeta by minus grad square psi, right? Zeta by minus grad square psi. So that means del t. So that means del t. So zeta. So everywhere, what we are doing, everywhere we are substituting zeta by grad square psi minus grad square psi, right? We are substituting these zeta terms by minus grad square psi because already we have derived from your from the consideration of stream function the zeta equal to minus grad square psi. So if we substitute zeta by minus grad square psi, so here we are substituting d zeta by minus grad square psi, d zeta by minus grad square psi, d zeta by minus grad square psi, and here also minus grad square psi. So what we can see del t of grad square psi minus del psi del y del x of grad square psi plus del psi del x del y by grad square psi equal to mu grad 4 psi mu grad 4 psi. Grad 4 basically this is a biharmonic. This equation is basically a biharmonic equation. So what is nu? Nu is your kinematic viscosity mu by rho. So what we have done here, we have done some algebraic manipulation. That's simply nothing. We are substituting zeta by grad square psi, and we write this equation by taking minus from here to here. A minus minus will be cancelling out, and this equation equal to nu grad 4 psi. So this is the standard form of the stream function equation, which you can obtain. That is basically the transport of stream function, which you can obtain from the vorticity transport equation. Is there any difficulties in understanding? Is that clear? How we have obtained this equation?
Yes, sir.
Sir, the velocity field can only be known from these equations.
Velocity field? No. From this equation, why we are deriving this equation? We are deriving this equation to calculate the velocity field because we do not know the velocity field a priori. So based on the boundary condition, we want to calculate the stream function equation. Once we have a stream function equation available with us, once we have a solution for the stream function available with us, so we can obtain the velocity field. This del psi del y del psi, because once we have calculated this stream function del psi value from these transport equations, we can calculate the velocity field v and u. That is the primary objective of solution of the Navier-Stokes equation, right? Because in a Navier-Stokes equation, why you are interested in Navier-Stokes equation? Because from the Navier-Stokes equation, we are interested to solve the Navier-Stokes equation. So what are the primary constituent of Navier-Stokes equation? What we want to solve the Navier-Stokes equation? We want to solve the Navier-Stokes equation to obtain the velocity field u and v, because this two-dimensional Navier-Stokes equation, if we see a Navier-Stokes equation, this Navier-Stokes equation contains the velocity field u and v. We want to solve this Navier-Stokes equation. We want to solve this Navier-Stokes equation to obtain the velocity field u and v. So that's why we have approached the stream function method. If we obtain the solution of the stream function psi, we could easily obtain the velocity field v and u, because v and u is a function of the gradient of psi only along the x and y directions. Is that clear now?
Yes, sir. Then how can we get the pressure field also?
Yes, I am coming to that. I'm coming to that. So that
Okay,
part
sir.
is up to this it is clear, right? Up to this is
Yes,
clear.
yes.
Okay,
Okay, sir.
okay. Okay, now very good question. Shivnath asked, how can we get the pressure field? That is the next topic. Determination of the pressure for viscous flow. How we can get the pressure field? We can easily obtain the pressure field once we obtain the stream function and vorticity field. That means if we have the stream function and vorticity field with us, we can obtain the pressure field. How we can obtain? Now, let us go back to the x momentum equation. X momentum equation. Let us go experimental equation. This is the experimental equation. This is the experimental equation. Okay. Let us see the experimental equation. The rho del u del t plus u del u del x plus v del u del y equal to minus del p del x plus mu del 2 u by del x2 plus del 2 u by del y2. This is the experimental equation. And this is our y momentum equation. Rho del v del t plus u del v del x plus v del v del y equal to minus del p del y plus mu del 2 v by del x2 plus del 2 v by del y2. So these are the primary equations. Now how to obtain the pressure field? Let us, because you know what we did in the stream function vorticity method, we get rid of pressure field, right? Because there was no sufficient method equations available for the pressure, then how we could get the pressure field? How we could get the pressure field? Because there was no sufficient equations for the pressure. So initially we get rid of the pressure field and we obtain the stream function and vorticity equations to calculate the velocity field. So once the velocity field available with us, that once we have obtained the velocity field, then we will get the pressure field. How? These are the x momentum equation, and this is your y momentum equation. Let us take a derivative x momentum equation with del x. So del x of this x momentum equation. Let us do del x of this x momentum equation. So del x of x momentum equation. The del x of del u del t plus u del u del x. So del x of that is del u del x whole square plus u del 2 del x del 2 u by del x2. Then v del u del y, that is del v del x del u del y plus v del 2 u by del x del y. We are simply taking partial derivative of x momentum equation with x. So this term minus 1 by rho del 2 p by del x2 plus nu, which is basically your kinematic viscosity, del x of del 2 u by del x2 plus del 2 u by del y2. So what we are doing here, we are taking derivative of x momentum equation with del x. Similarly, again, what we are doing, following the similar procedure, we are taking differentiated, or we are taking derivative of the y momentum equation with respect to y. So what we are doing here, similar procedure, del y of del v del t plus v del u del y, that is del u del v del y whole square, similarly plus v del 2 v by del y2 plus u del v del x, so del u del y plus del v del x plus u del 2 v by del x del y equal to minus 1 by rho. Here del p del y term is there, so del 2 p by del y2 plus nu del y of del 2 y del x2 plus del 2 y by del y2. So what we are doing here, we are taking derivative of x momentum equation, partial derivative of x momentum equation with respect to s, that is del x, and partial derivative of y momentum equation with respect to y, that is del y. We are simply taking partial derivatives of x momentum and y momentum equation. After taking those derivatives, x momentum and y momentum equations, that is equation number 6 and 7, we are adding those two equations, that is adding 6 plus 7. So if we add 6 plus 7, so what we will be getting here, that is del x. So if we see the first term, del x of del u del t and del y del v del t. If we take del t common, what will have del u del x plus del v del y. Okay. Then what will have del u del x whole square plus del v del y whole square. Fine. Then what is there? Del v del x del u del y del u del y del v del x. So 2 twice 2 del v del x del u del y plus what we have then u. If we take u common, u and u common, what is there? Del 2 u by del x2 plus del 2 v by del x del y. If we take v common, so del 2 u by del x del y plus del 2 v by del y2 equal to minus 1 by rho del 2 p by del x2 plus del 2 p by del y2 del x2 plus del 2 p by del y2 plus nu del x del 2 u by del x2 plus del 2 u by del y2 plus nu del y del 2 v by del x2 plus del 2 v by del y2. Is there any understanding, either in difficulties and understanding in this slide? Is that clear? Very straightforward.
One means means okay.
Hmm? Any
Uh,
difficulties in understanding?
okay, we differentiated with respect to x. Okay, y.
We differentiated x momentum equation with respect to s and y momentum exponent with respect to y, and we are adding these two equations after getting it differentiated by x and y,
Huh.
and we are doing some algebraic manipulations. Is that clear?
Okay.
Okay.
Okay, sir.
Any issue? Anyone? What is that guy? He left. What is that guy? I was. Deep is there. Mainak is there. Uh, is left. Okay. Okay. So yes. Okay. So there is some issue is there. It should be V. It should be V. Okay, I think you have understood this slide. How we are getting, what we are doing here. Yes.
Yes.
So very straightforward. Taking derivative with respect to x of x momentum equation, taking derivative with respect to our y momentum equation, and we are adding these two equations after taking derivatives.
Huh.
Okay,
Yes.
and
Yes.
we're just simply manipulating.
Mhm.
Now, next slide. What next slide? Little bit of more algebraic manipulations. Now let us see. We have del t of del u del x plus del p del y plus del u del x whole square plus del p del y whole square plus 2 del v del x del u del y plus u this plus v in this term equal to minus 1 by rho del 2 p by del x2 plus del 2 p by del y2 plus nu del x of this term plus nu del y by this term. So what we are doing again then, so this is the equation, the del t by del u del x plus del p del y plus del u. I have again written this equation to bring more clarity in understanding that del t of this equation, that's the exact equation what I have written here. Same equation I have written here. Same equation I have written here. Already you know this equation. Now let us do some more manipulations. So this is the first term which is remain intact. We're not doing anything with this term. So now what is this? Del u del x plus del v del y whole square. That's a square plus b square. What is this? The in a square plus b square we can write a plus b whole square minus 2ab. A square plus b square we can write a plus b whole square minus 2ab. That is del u del x plus del v del y whole square minus 2 del u del x del v del y. Right? We can do that. A square plus b square equal to a plus b whole square minus 2ab, that we can write. So this time is there, do del v del x del u del y plus u. If we take del x common from these two expressions, if we take del x common, so what will be getting? Del x of del u del x plus del v del y. Similarly, v, if we take del y common, what will be getting? Del u del y del u del x plus del v
Del u
del
del
y.
x
Yes.
same expression. Huh.
Sorry,
Yes, means the
any
I,
doubt?
no.
Mhm. Now tell me. If you have any doubt, please tell me.
No,
What is
I
the
was
doubt?
saying that within the bracket the same expression will come. Del u del x plus del u del y.
Exactly. So if we take del s common, within the bracket, same expression will come. Same algebraic, simple algebraic manipulation. High class 10 plus 2 algebraic manipulations. Not maybe less than that.
Huh.
So minus 1 by rho here, or del 2 p by del x2 plus del 2 p by del y2 plus nu. Uh, New what I have written here, I think I have done some mistake here. What mistake I have done? I have to write del 2 this term. This term was missing. I have this term is missing. This term is missing. This term is missing. Yes, now it is okay.
Del two. Yes. So,
Now see this equation, this expression. You just take del 2 by del x2 and take del 2 by del
huh.
x2. What will have? del 2 del x2 del 2 del x2 del 2 del x2. So del u del x plus del v del y. Right? Right? Is it clear? Let us consider this term and this term. If we take del 2 del x2 common, del 2 del x2 common, then what we will have? Del u del x plus del v del y. Right?
Yes, into V. Yes.
Into new, not v. It is
Uh,
new.
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 Hmm.
Yeah. Similarly, if you take this expression and this expression, if you take del 2 del y2 common, del 2 del y2 common, then what we will have? Del u del x plus del v del y. If you take del 2 del y2 from this expression common and del 2 del y2 from this expression common, so what will have? Del u del x plus del v del y. Right? Straightforward. Clear? Is that clear?
Yes, sir. Yes.
Yes, sir.
Now, what we can do further? From continuity equation, what do we know? From continuity equation, we know that del u del x plus del v del y equal to 0. From continuity equation, this is a form of continuity equation. So if you put del u del x plus del v del y is 0, where there is a term, where in those expression, when there is a term del u del x plus del v del y, because from continuity equation this will be automatically 0 if you put 0 here and 0 here, because these are the 0 values from the continuity equation. What we will have then? Minus 2, because this is 0, 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 and this is 0. So all these terms will be automatically 0. It will be automatically 0. These are 0, this is 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 1 0, this one is also 0. So then what will have? You will be left with minus 2 del u del x del v del y plus 2 del v del x del u del y. These are the two terms you will be left with. You will be left with equal to minus 1 by rho, because all these terms are 0. So you are left with this term, and this term. You are left with minus 2 del u del x del v del y plus 2 del v del x del u del y equal to minus 1 by rho del 2 p del x2 plus del 2 p del y2. That means we can write del 2p del x2 plus del 2p del y2 if we take row on the left hand side, or you can write this one as left hand side and this one as right hand side. That is 2 row del u del x del v del y minus del v del x del v del y. Okay, so that means 2 row. So you can write u as a del psi del x and v as a minus del psi del y. So you can write as del 2 psi by del x2 del 2 psi by del y2 minus del psi del x, because it will be v will be your del psi del x and u will be del psi del y. So you will be left with del 2 del psi del x del 2 psi by del x del y. Again, I have done a mistake. I'm doing mistakes or mistakes. It will be del 2 psi. It will be del 2 psi. I'm doing mistakes or one mistakes. Yeah, del 2 psi by del x del y. That is, you are simply what you are doing. You are simply writing u as a del psi del y, v as a minus del psi del x. So simply you are writing those equations, and if you write v equal to minus del psi del x, so it will be del 2 psi by del x2. So minus minus plus, then u is a del psi del y, del 2 psi by del y2. So you are taking those in the right before this negative expression. So it will be this minus u is a del 2 is u is a del psi del y, that is del 2 psi by del x del y. V is a minus del psi del x, that is del 2 psi by del x del y. Before that there will be minus. You are taking this expression in the right hand side. So del 2 psi by del x2 del 2 psi by del y2 minus del 2 psi by del x del y. So there are two terms. We will be appearing del 2 psi by del x del y and del 2 psi by del x del y. That will be del 2 psi by del x del y whole square, because those are multiplied whole square. So that means you can write this expression as grad square p equal to 2 rho del 2 psi by del x2 del 2 psi by del y2 minus del 2 psi by del x del y whole square. So this is the equation of pressure. Is that clear? Is that clear? Anyone has any question? Is that clear?
Yes, sir.
Have you understood how we have obtained this special equation?
Yes, sir.
Okay. Okay. So, fine. Now, who to ask?
আর ফাইনাল রেজাল্টটা একবার দেখাবেন, মানে ফাইনাল লাস্ট রেজাল্টটা del to p.
Is
Okay,
that
sir.
clear or no? Is that clear? Very straightforward.
Hmm.
I have simply substituted the expression of u and v by del psi del x del psi del y.
Hmm.
Now, yes, Shravan.
Yes, sir.
Tell me how we'll get the pressure field. Given this expression, how will be getting the pressure field? How will be getting the pressure field?
Into x to সাইটাকে
Okay.
putting psi
Joy Manna. Joy, are you there or left? Maybe some internet connectivity issue. Yes. Joy, are you there? Oh, no. Subjit. Subjit,
Yes, sir.
how can I get the pressure field?
Sir, first we x moment equation we also derivatives by del by del x.
No, actually, see, Shivnath asks that how I can get the pressure field. So I have derived the equation of pressure field. Del to psi, del to p equal to 2 rho, this equation. So what is the purpose of deriving this equation? I cannot be purposeless, right? So my question is, how we can get the pressure field? Why you have done so much mathematics and obtained this pressure equation? So how we can get the pressure field? Anybody? Deep Chatterjee?
From psi value we have to compute, then after that maybe
psi value থেকে
From?
Sorry.
Yes.
if we
From psi value?
if we can find the psi distribution, if we know, then from that value after differentiating we can get the value of
Exactly.
pressure field.
Exactly. That is the answer. So, now we can see we have obtained the psi value, right? Team function vorticity method. We have solved these two equations and we obtain the psi value, right? If we obtain the psi value, we can solve this equation because this right hand side expressions, all the values are known. Psi values are known, right? If psi is known, if we can solve this special equation, which is called Poisson equation of pressure, basically is a Poisson equation, del 2 p by del x2 plus del 2 p by del y2. If you can solve this equation, we can obtain the pressure field easily because these expressions are known, these values are known. Is that clear to everybody? Ogneshwar, is that clear?
Yes, sir. Yes, sir. Sir, I did not
Understood?
understand. Sir,
Which one? Tell me.
Sir, what is the? So can you please
What
show
is
me the
that?
equation once?
Okay. Yes. So my question was how we can get the pressure field, and Deep correctly answered that we have already solved the steam function field, right? From
Yes,
the
sir. Yes,
steam
sir.
function velocity equation, already we have solved steam function field, and
Yes,
this
sir.
right hand side
There's an
expression
equation
values are
between
known.
steam and flux.
Yes, yes. These are already known values. If these are known,
Yes, sir.
if you can simply solve this pressure equation, you can get the pressure field, right? Is it
Yes, sir.
clear?
Yes, sir. Yes, sir.
Okay.
Then
Now we
just
can
put the value
appreciate.
of this function. Del 2 by y by del 2
Yes,
psi by
yes.
del x2 and del 2 psi by del y2.
Exactly, exactly. Because all are known, all are known. At different grid points, all values are known. So simply solve this pressure equation, you can obtain the pressure field. Is that clear to everyone?
Yes.
Yes, sir.
Hmm.
Yes, sir.
Okay, okay. So that is the primary objective of deriving this equation to obtain the pressure field, pressure equation. Now there may be another situation which is called the creeping flow situations. That is how we can apply the stream function, because already we have seen we have applied the stream function velocity method when there is any type of flow situation, but there is a special type of flow which is called the creeping flow. I think everybody knows what is creeping flow.
Sir, can you explain
You
it?
people, you people have studied in your fluid mechanics 2 class, right? Creeping flow, or you have forgotten?
No, sir. Keeping
No,
flow.
sir.
Sir,
You
I
have not
think it was
studied.
not there, sir.
didn't study. Keeping flow.
Okay, you have not studied. Okay. Okay, let me explain what is creeping flow. Creeping flow is a particular type of flow where the Reynolds number is very, very small. For example, if you see the glacier, okay, the glacier, how the glacier is flowing from one point of mountain to another point of mountain. Maybe how it is flowing from the peak to crest, how the glacier is flowing. But the Reynolds number is very slow. Reynolds number is order of 10 to the power minus 2, order of 10 to the power minus 3. So those kind of flow basically are called the creeping flow. For example, flow of blood in a blood capillary. Okay. So where the Reynolds number is very, very small, those kind of flow basically are called the creeping flow. For example, flow in a porous media. Porous media means sponge, like sand, porous sand, clay, all are basically porous media. So how the fluid is flowing through the through sponge or through clay, those kind of fluid motion are called the porous media fluid motion. For example, flow through a macro channel, because there are certain classes of flow when the channel height is very less. Suppose you have a channel, two-dimensional channel, where the height of channel is, for example, 50 micron or 20 micron. Those kind of channel are called basically micro channel. So the flow through those type of micro channel are called basically the creeping flow situation. So there are various applications of creeping flow. Drug delivery. Suppose if you want to deliver drug to a human body, how we can deliver? Basically there are certain kind of lab on a chip mechanism. So in a particular chip, microfluidic chip, you can basically generate a certain classes of macro channels or certain types of macro channel to perform diagnostics, lab diagnostics, which is basically done in pathological laboratory. So lab diagnostics, those are basically lab on a chip applications. There is fluid mechanics, they have got huge application in lab on a chip applications. So all in those applications, basically fluid motion or flow of fluid is very, very, velocity of the fluid is very, very small. Order of 10 to the power minus 3 if you calculate the Reynolds number. Suppose how the water is getting sucked by the stems of big tree, how the fluid is flowing through the suction caused by a big tree through their stem, which is basically capillary motion. So those kind of motion, the fluid motion velocity of the fluid is very small. Those kind of fluid basically is called the creeping flow situation. Okay, understood? What do you mean by creeping flow?
Yes, sir.
Okay. Suppose bacteria motion. Suppose you have a bacteria, how the bacteria is moving. Okay. So those kind of motion is called the creeping flow motion. So in this creeping flow motion, if you
Sir,
want to, yes, yes.
that means the pathogenic means lab drug the case of drug injection. Can you please repeat that example again?
Okay, are you interested in knowing this pathogenic applications?
Is I'm wanting to say whether it
Uh-huh.
has any significance in COVID related
Okay. So there are. If you are interested, we can have a separate discussion on that because it is a big subject. You just know that in a pathogenic applications, one can apply this macrofluidic technique we call drug delivery technique. You can say lab on HE application, macrofluidic application, lab on CD application. Basically, those are the pathological applications where we can generate one we can basically generate small macrofluidic chip in a small area, maybe in a CD, and we can perform some pathological tests. Basically, those are called lab on a CD application.
Okay.
Okay. So we can, if you are interested, we can discuss separately on that because there's a big subject and it requires thorough discussion. Okay. You just know that those applications, creeping flow is very much relevant. In those creeping flow applications, basically that Reynolds number is very small, and since the Reynolds number is very small, we can neglect the transient term and convection term in the Navier-Stokes equation. So one form of creeping flow, you might be aware of this term, Stokes flow, Stokes law, Stokes drug. You know, right? Stokes flow. Do you know Stokes flow? Have you heard of this term Stokes? Stokes flow?
Yes, sir. Stokes flow. I have heard.
Okay. The Stokes flow is not. Yeah. Stokes
Sir,
flow is nothing but the creeping flow. Yes. Tell me.
sir, I don't know the Stokes flow, so can you explain
Stokes.
a little bit?
Yeah. Either creeping flow or Stokes flow. Reynolds number is very small. Okay. So in those applications where Reynolds number is very small, we can neglect the inertia terms in Navier-Stokes equation. That is the inertia term. That is the basically this convection terms, which are called basically nothing but the inertia terms, and the transient term. Basically, those type of flow are steady, and convection term can be neglected. Okay, so I think we have derived this equation previously. This is the equation we have derived. This is the equation from the stream function velocity equation. We have derived this equation, right? This equation we have already derived. So in this equation, this is your transient term, these are the convection term. So in those types of flow, creeping flow situation, we can neglect time dependent term and the convection term. These are the terms we can neglect. So because Reynolds number is very small, Reynolds number is very small, so we can neglect these terms. Basically, transient term will be 0, tending to 0. Convection terms will be 0. So only we have a diffusion term, that is nu grad 4 psi. So for the Stokes flow, if you want to solve the Stokes flow, or if it's from the creeping flow situation where the Reynolds number is very small, the governing equation that basically that we need to solve for calculating or for obtaining the stream function in a fluid domain, that is grad 4 psi equal to 0. This is the equation grad 4 psi equal to 0. So where grad 4 psi, this is the equation that we can obtain, grad 4 psi equal to 0. This equation is called the biharmonic equation because here psi to the power 4 term is appearing, and that's why it is called the biharmonic equation. And again I have done one mistake. So grad 4 is equal to where grad 4 where get4 equal to del psi del to the power 4 by del x4 plus 2 del square by del x square del y square plus del to the power 4 by del y4. This is the form of grad 4. This is the form of grad 4. So for creeping flow situation, we need to solve this biharmonic equation, and basically this is also linear equation because since the coefficients are constant, it is not a function of x and y, and but we need to solve this biharmonic equation to obtain the solution for the stream function for creeping flow situation. So for creeping flow situation, basically we need to solve this biharmonic equation to obtain the solution of stream function. Okay, any doubt on this slide? Anybody has any question?
Sir, why it is called biharmonic equation?
Because this fourth time is appearing. 4. That is
Yes,
called the biharmonic equation. Grad squared is harmonic and grad to the power 4. Poisson equation, what is that? Poisson equation is grad squared, right? This Poisson equation. This is a Poisson equation. Is it grad square, right? Grad square
yes, sir.
p. Now biharmonic means again we are taking grad square. So grad to the power 4. That's why it's called the biharmonic. The Poisson equation basically it's a harmonic equation. One form of Poisson equation, the Poisson equation sometimes called the harmonic equation. And get to the power 4 equation because it is the harmonic to the power some. Again we are taking grad square operator on this grad square psi. That's why it's called the biharmonic equation. Clear? Is that clear?
Sir, when you were explaining the Stokes flow, I lost my internet. So could you please explain the Stokes flow?
No, Stokes
I
flow
heard
and
sounds.
Stokes flow and creeping flow are same actually. You can call
Oh,
either creeping flow or Stokes flow. Both are equal.
okay, sir.
Okay. Anybody has any doubt?
তোকে ভালোবাসতো কিন্তু কিন্তু তোকে ওই মেরে
Okay.
Yes, sir.
Okay.
Yeah, yes,
Shall I continue or shall I stop it? I think if people are exhausted with the questions, right?
sir, one
Yes, sir.
question is,
Yes.
sir, again, please display the last slide, creeping flow slide. Yes, for steady flow. As means the derivative with respect to the distance y at the 0 means time based derivative is 0 for steady flow.
Yes. What is your doubt, Shravan?
For steady flow, the time derivative becomes 0. Yes, but why are equating 0 the derivative with respect to distance?
Okay. Is that distance or variable? X and
Means,
y variable.
yes, means x and y.
Yes. For the creeping flow, what is the thing that we have discussed? What I was discussing? The creeping flow is a steady and inertia terms can be neglected. Okay. So
Okay.
what are the inertia terms in this equation?
Steady inertia.
What do you mean by inertia term? What are the inertia terms in this equation?
Yeah, means the rest of means the derivative with respect to the variables x and y.
No. What do you mean by inertia term?
Sir, the second and third term.
Exactly. So in Navier-Stokes equation,
Second, second.
you should understand. Yeah. Suppose in the Navier, this is the Navier-Stokes equation, right? So what are the inertia terms here?
So it is U del U del X plus V
Del-
del Y.
Yes, yes, yes. These are the inertia terms, right? These are the inertia term. These are the transient term. These are the diffusion term.
Temporal.
No, no. I think you should understand Navier-Stokes equation clearly. I don't know. There's some problem in understanding. Let me explain it. Okay, you should keep this in your mind. Navier-Stokes equation. Navier-Stokes equation. Navier-Stokes equation. In Navier-Stokes equation, first one is called temporal term. Temporal. Second one is called inertia or convective term. Third one is called pressure gradient. And last one is the diffusion term. Okay?
Okay.
Right. So this one is temporal term. This one is inertia term. This is your pressure gradient. And this is your diffusion term. So for low Reynolds number flow, your temporal term and since the flow is steady, your temporal term is 0 and your inertia term is neglected. When the Reynolds number is very, very small. Right? Very, very small. That means you have only diffusion and pressure term. You have only diffusion and pressure term.
Diffusion and pressure terms.
Equal to 0. But in vorticity equation, you don't have any pressure term. Right? Because we get rid of the pressure term. That's why we have only diffusion term, which is 0 for creeping flow. Reynolds number is very, very small. So what is diffusion term here? So let us corroborate what I have written or what I have explained in this slide, in this paint platform. So this is your temporal term, this is your inertia term, and this is your diffusion term. So for the creeping flow is steady. So your temporal term is 0 and inertia terms are 0. So this is inertia term which is 0, this inertia term is 0. These are the neglected. That means you have only r to the power 4 equal to 0. This is a biharmonic equation. For the creeping flow situation, you have only the form of equation that you need to solve to obtain the stream function is the biharmonic equation, which is r to the power 4 equal to 0. Is that clear now? Yes or no?
Yes, sir. Yes, sir.
Okay.
Any doubt?
Sir, could you please explain this polymer and fluid expression here?
Sorry?
Yes, sir. I mean, how things are applied in polymer and food extrusion?
Okay. Application, no? Polymer flow, basically nothing but your creeping flow situation. Suppose you have a polymer, suppose you have a polymeric fluid. Suppose you have a polymeric fluid. Polymer means suppose paint, Asian paint, for example, some kind of paint. The paint, suppose you have a paint which is flowing in a pipe. Suppose this is a pipe, this is a pipe, this is a pipe, and through this pipe, paint is flowing. Suppose paint. Now, if you want to solve this problem computationally through CFD techniques, then the governing equation for this situation, if you want to solve this stream function vorticity method, is your biharmonic equation. get to the power 4 psi equal to 0.
Sir, does
Okay.
this paint liquid flows very slowly?
Uh-huh. I'm not able to
Uh,
understand you.
yes, sir. I asked about that. Does this paint liquid flow very slowly?
Yes, it is very slowly actually. If you want to give an external pressure, high pump or high pumping velocity, then it may flow faster. But in general, the flow velocity is very slow. Okay. Compared to the water or Newtonian fluid, the flow of pump or slurry, their velocity is very small in compared to the Newtonian fluid. Okay.
And sir, the food extrusion part.
Food processing industry, for example, food processing industry, where basically there is a there is a manufacturing. If you want to suppose in the food processing industry, there is a continuous manufacturing of jam, jelly, those kind of industries. Basically those are kind of polymeric fluid. These are basically non-Newtonian type of fluid, non-Newtonian fluid, and those in those applications, when jam and jelly is flowing through some industrial manufacturing unit, the velocity, fluid velocity is very small in compared to the Newtonian case. Suppose water or maybe other Newtonian fluids which follows the Newtonian of it. There is the application of this bioharmonic. Those kind of flow basically are keeping flow application. Similarly, in a porous media, suppose you have a sand, you have a bucket of sand, and you just pour water from the top. If, now the what will happen? The fluid will slowly penetrate through the sand stock stand to the bucket of sand. Now it will slowly move inside, and the velocity of fluid generally very small compared to the velocity of fluid in a space when there is no existence of sand, or it is sand free motion, or so there is no sand. Okay, so in that case, the Reynolds number is very small. So that is called the flow through porous media. Suppose absorption of some absorption media. Suppose there is some absorption of fluid in some through some membrane. So in that application, that Reynolds number generally very small, which is basically lies in the creeping flow region.
Sponge-like bodies.
Yes, something like that.
Okay, sir, thank you, sir.
Okay, shall I stop the class today, or and discuss the remaining things in the next class, or I shall proceed? What shall I do?
Happy birthday to you.
Shall I start the class today? Okay. Maybe I can discuss maybe another 2 slides. Then another 2 or 3, because I have another 4 slides. Shall I discuss today, or because I have only finished very small part of it.
Yes, sir. You can finish the next 2 slides.
Okay. Now we have discussed up to creeping flow. Then one important point that we have missed out, that in this steam function and vorticity equations, you have these two equations, steam function and vorticity equation. One equation is your steam function equation, which is grad square psi equal to minus zeta. Another one equation is vorticity equation, rho del d zeta dt equal to mu grad square zeta. So these are the two equations. There's two equations you need to solve. But for the solution of these two equations, what do you need? What do you need? You want to solve these two equations?
So the viscosity and density.
No. What do you need?
Sir, the vorticity.
No. If you want to solve these two equations in a computational domain, what do you need?
These are first two.
Yes, because these are two equations. No, these two equations you need to solve, right? These two equations you need to solve. But even to solve these two equations, what
We
do you
need the
need?
boundary conditions.
Very good, very good. Yes, absolutely correct. You need the boundary condition. So that is the primary objective of this discussion. That if you want to solve these two equations, we need the boundary conditions. Without having the proper boundary condition, you're not able to solve these two equations. Now, for the stream function, so you already have the boundary condition because in any case, in any domain, velocity will be specified. So for a particular inlet velocity, you want to solve the problem. If the velocity is specified, from the velocity specification value, you can obtain the stream function value and you can solve it. But what about the vorticity boundary condition? Understood? So once we have the stream function available, you can also calculate the vorticity because velocity is specified. Suppose you have a velocity specified, vorticity. So velocity is specified. From the specification of velocity, you can obtain the stream function as a boundary condition. And with the boundary condition, you can solve. So if you have the stream function available, if a velocity is specified, you can also obtain the vorticity value, vorticity field. So with the stream function and vorticity, you can solve the governing equation of stream function and vorticity, these two equations. But my question is, what will be the boundary condition of the vorticity at the wall? That is the primary objective. So what will be the boundary condition at the wall?
Zeta is equal to 0.
Zeta equal to 0 is boundary condition at the wall if velocity is 0. But what will be the boundary condition at the wall for vorticity? Okay, so that we need to discuss. So there are two situations that I will be discussing. There are two situations how we can calculate the boundary condition for the vorticity at the wall. So let us consider case A where the wall is stationary and non-sloping. Non-sloping means wall is horizontal with the x-axis. So it is a horizontal wall. It is not making an angle with the x-axis. So this is the x-axis, this is the y-axis. This wall, which is not making an angle with the either x or y-axis, is a horizontal wall. So for the horizontal wall, to determine zeta, to determine vorticity, what we need to do, suppose there are 2 points, grid points, grid point number 1, which is I1, and grid point number 2, which is I2. Okay, there are 2 grid points. So you want to calculate the vorticity boundary condition at the grid point, at these grid points. So what you can do, you can, the usual practice in this method to calculate to obtain the vorticity boundary condition for the stationary and non-sloping wall. That is, what you need to do, you need to perform a Taylor series expansion of psi I2 about psi I1. So if you write Taylor series expansion of psi I2 stream function at a point I2 about a point I1. So what will be the stream function expansion? Psi I2 equal to psi I1 plus del psi del y at I1 into delta y. If delta y is the distance, vertical distance between these 2 points I1 and I2, plus delta y square by 2, del 2 psi by del y square at I1 plus order of delta y cube. Right? This already you know. Is that clear?
Yes,
Is
sir.
that clear? Okay. Already you know. So what do you do? What do you know? Because if the distance between I1 and I2 points is delta y, so psi I2 can be written as psi I2 is psi I1 plus del psi del y at I1 delta y plus delta y square by factorial 2 del 2 psi by del y2 at I1 plus order of delta y cube. This is the expression, Taylor series expansion. So what we are doing? We are writing a Taylor series expansion of point I2 with about a point I1. Taylor series expansion. Now the no slip wall is no slip, right? Wall is no slip, velocity is 0. That is I1 is 0. I1 velocity at point 1 I1 is 0. At this point is I1 is 0. If I1 is 0, U what do you mean by U? U is del psi del y. So del psi del y at point I1 is 0. So you are writing del psi del y at I1 is 0. This term will be 0. This term will be 0. So that means therefore if del psi del y equal to 0, Therefore, you can write del 2 psi by del y2. That is del 2 psi by del y2. Del 2 psi by del y2 equal to del u del y. Del u del y. Simply what you are doing, you are taking derivative with respect to y, del y. Del 2 psi by del y2 equal to del psi del u del y. Del 2 psi by del y2 equal to del u del y. So del u del y at point I1. Now zeta as vorticity at point I1. So that is our primary objective. So what will be the vorticity value at point I1? Because stream function values are known. Because at wall stream function values are known. So what is the vorticity value at point at the wall at I1? High zeta I1. Zeta I1 is nothing but del v del x minus del v del 1 I1. Del v del x at I1. Del u del y at I1. This is the definition of zeta. Already we have discussed at point I1. Now for non-porous wall, V equal to 0, because here no sleeve wall means U0 V0. Okay, no sleeve wall means U0 V0. If there is a porosity in the wall, then V may not be 0. But here we are considering wall is solid, so there is no porosity in the wall, so V is also 0. Yes, any question? Any question? Okay. So we can write zeta I1 equal to del v del x minus del u del y. So V is also 0. V0 means del v del x equal to 0. V0 means del v del x equal to 0. So that means zeta I1. So we can write in this equation zeta I1 equal to minus del u del y. Minus del u del y. V equal to 0. It is del v del x equal to 0. V equal to 0 and del v del x is equal to 0. The zeta I1 equal to minus del u del y. That is del u del y means del 2 psi by del y2. So minus del 2 psi by del y2. Right? V equal to 0 means del v del x is 0. So in this equation, del v del x will be 0. So we can write zeta I1 as minus del u del y at a point I1. That is zeta I1 equal to minus del 2 psi by del y2. Minus del 2 psi by del y2 at point I1. Okay. So now let us go to the expression. What is the expression? Psi I2 equal to psi I1 plus del psi del y I1 delta y plus delta y square by 2 del 2 psi by del y2 at I1 plus order of delta y cube. So that means psi I1 plus del psi del y is 0. That already we have seen. Del psi del y is 0. Del psi del y is 0. Del psi del y is 0. 0 into delta y plus delta y square by 2. This term is, what is this term? Is minus this term minus zeta I1 plus order of delta y cube. So if you take algebraic manipulation, if you take this term and divided by delta y square by 2, delta y square, so we have zeta I1 equal to twice of psi I1 minus psi I2 by delta y square plus order of delta y, because delta it will be divided by delta y square. The delta y cube will be cancelled, so it will be delta y, order of delta y. So we can calculate psi I1, that is psi 1. So zeta I1, that is the vorticity value at wall, which is the point at I1 point, is nothing but psi I1, the stream function value at the wall minus stream function value at a distance of delta y away from the wall, vertical distance delta y away from the wall, the next bit point, that is psi I2 by delta y square plus order of delta y. This is the expression of zeta y. It is the vorticity value zeta I1 at the wall. So in this way you can calculate the vorticity value at the wall. Any difficulties in understanding? This is okay.
For non-porous wall, component, sir, for
Sorry?
non-porous wall, the x component is should also be 0 because the flow is at no slip there. So
No. For non-porous wall, there will be this type of flow. U may be 0, but V is not 0. Okay. Okay. If the wall is solid, if the wall is solid, then there is no velocity component. U and V are 0.
আরেকটা আগে আগে করতে চাইছিস
If the wall is porous, if the wall is porous, then there may be a V component of velocity. But U component is 0. Understood? The differences between porous wall and non-porous wall.
Uh,
This
if
is a
it
porous wall.
that means it is a solid wall, then the component of U should also be 0.
Which one?
Uh, I said that if it is a non-porous wall, that is a solid wall, then the U component also should be 0.
Definitely. If non-porous wall, UV are 0. This no slip boundary condition. Already you have discussed. No slip.
Yes.
No slip. No slip. But porous wall, there will be a U component will be 0, but V component may be there. Suppose you have a bucket of sand. This is a porous wall. You have put a water on it. Suppose water. So what will happen? Water will slowly, gradually penetrate, right? So V component velocity will be 0, but water will not go in this way. U component is 0. Okay.
Then why in the last slide for non-porous wall we just have put the V component as 0?
Which one? This one. Non-porous means basically it is solid wall.
Then said the component of U should also be 0.
U is 0. Definitely U is 0. But del U del X is 0. But del U del Y is not 0. Del U del Y is not 0. Del U del X is 0. This gradient is 0. But along vertical gradient is not 0. Why?
Okay,
Why,
sir.
right? Why? No. You should ask why. What do you know about boundary layer equation? Boundary layer. Show over a flat plate. Del U del Y is there, right?
Yes.
But del U del X
Del U del X this direction.
is 0. If you perform the order of magnitude analysis, Glaciers order of magnitude del U del X will be 0, right? Order of epsilon. Only del U del Y will be 0, which is basically nothing but your shear stress.
अच्छा हाँ plus हाँ
Okay. That's why this component will be 0. It will not be 0. Del U del Y will not be 0. But del U del X may be 0. Similarly, del B del X may be 0, but del U del Y will not be 0.
Sir, could you please explain it again?
Which one? This one? This one?
Yes, sir.
Have you studied in a boundary layer? In a boundary layer, what is there in the boundary layer? Suppose it is your flat plate, right? Flat plate, and there's a problem actually. I don't have stylus pen with me. See how I can. So this is your boundary layer,
Okay.
right? Fluid is flowing. This is a boundary layer. So inside the boundary layer, what is there? Del U del Y is 0. Is not 0. It will be there. It is very high. But order of del U del X is order of epsilon, which is very small. You have not done this order of magnitude analysis in the boundary layer equation.
yes
Yes, sir. We have done.
yes
So del U del Y is not 0. It will be very high because it is basically a manifestation of shear stress.
Yes, sir. Yes, sir.
Shear stress will be only limited within this boundary layer, where it is a function of del U del Y only. Clear?
Yes, sir.
That's why del U del Y is not 0.
Okay, sir.
It is not 0. Now it is understood.
Okay, sir. Yes,
Now
sir.
this expression is understood. How we are getting this vorticity value at the wall.
Yes, understood, sir.
Very straightforward. Okay. Now we have seen that how we can get the vorticity value of wall. Now maybe we have another situation that so we can write in general. So it is a I have written as a in a simplified form. This is the form. Now we can write in general. We can write zeta s, that is the vorticity value at the wall, which is basically 2 psi s minus psi s plus 1 by delta n whole square plus order of delta n. What is psi s? That at the wall, steam function at the wall, and this is, you know, there is an additional value psi I1 and I2. So psi s plus psi minus psi I plus s plus 1. There is an additional value by delta n. There is a delta n, basically the distances, vertical distances between s and s plus 1. So here it is delta y. So psi s minus psi s plus 1 by delta y whole square, the delta n whole square plus order of delta n. So this is a general form of this expression. So now you may have a situation, the wall is not stationary, it is moving with a velocity u, right? You may have a situation when the wall is not stationary, it is moving with a velocity u. Then what will be the value of vorticity at the wall? So in that case, if we perform this similar kind of analysis, I think that this should be left as an exercise. If you perform this similar kind of exercise, similar kind of analysis, when the wall is moving with a velocity u, and is a non-porous, that is v equal to 0, and it is moving with velocity u, you can obtain an expression of vorticity value at the wall, which is psi ij. You can write ij, basically j basically at the point at the wall. It may be 1j or maybe I1, whatever you call it, but better to call it 1j. That vorticity value at the wall as 2 psi ij plus 1 minus psi ij minus u delta y by delta y square plus order of delta y. So please do this in your home. This has left as an exercise, and if you can perform similar kind of analysis for a moving wall, you will obtain an expression of vorticity at the wall as 2 psi ij plus 1 minus psi ij minus 2 u delta y by delta y square plus order of delta y, where ij are basically ij is the steam function value of steam function at the wall, and ij plus 1 is steam function at a distance, vertical distance delta y from the wall. So this is the expression, and you should, if you can perform the above analysis, similar kind of analysis, you could obtain this expression easily. Okay, clear? Is it clear? Or any doubt? You just do it, you can obtain this expression. Now, what will be the vorticity boundary condition at the corner? So let me explain it in detail. At the corner of a block, what do you mean by corner of a block? Suppose you have a domain something like this. Suppose you have a domain. You have a domain something like this. This is a wall, and this is another wall, and in between there is a corner. Okay, this is the corner. Then what will be the boundary condition about the, because for this wall you may have vorticity boundary condition that similar to the method that already we have discussed in the class. You may obtain a boundary condition for the vorticity at this wall. Similarly, for this wall also you can obtain a boundary condition about the vorticity. But what will be the boundary condition of vorticity at this corner? Okay. Now please keep this in your mind. If you perform steam function vorticity method for the CFD analysis in a domain, there is a suppose something like this. Suppose there is a fluid which is flowing in a domain. It is going out in the domain, something like that. Fluid is coming here, and it is going from this here, from here. And if there is a corner, so there is the existence of a corner point. What will happen? In that case, the boundary condition of vorticity will be very much difficult to implement, because at the corner point velocity gradients are singular, so velocity gradient does not have any continuity. So in general, for CFD calculation, we neglect the vorticity boundary condition at the corner. So at the corner, basically we neglect the vorticity boundary condition because vorticity does not have any proper boundary condition at the corner. So vorticity boundary condition at the corner is neglected, and we refine the mesh near to the corner. If we refine the mesh near to the corner, if you can refine the mesh near the corner, we can afford to neglect the velocity boundary condition at the corner and obtain the correct solution of the velocity field inside the domain. Okay, clear?
Okay.
Okay, so let us stop the class now, and in the next class I will be solving one example problem, how one can apply stream function velocity boundary condition for the solution of a flow problem inside a two-dimensional domain. Okay, so let me stop the presentation now, and also the recording now.